Today we are going to learn about a special right triangle, a 45, 45, 90 triangle, also known as half a square, or a right isosceles triangle. So we're going to look at this. Where does this s squared to 2 come from? That's what we're going to really figure out today. So if you look at ABCD and it's a square, and all the side lengths are 1, all right. What type of triangle is ADC? Well, since it's a square, I know this is a right angle. And if you look, I'm cutting these 90s in half. So half of 90, this angle's got to be 45 degrees. And then this angle's got to be 45 degrees. So this side of the triangle is 1. This side of the triangle is 1. So two sides are equal. And these are both 45-degree angles. So this is an isosceles triangle. And it's a right isosceles triangle because that's a 90-degree angle. So how could we find the length of the diagonal? Well, that's a right triangle, 1, 1, and I don't know the hypotenuse. So we could just use the Pythagorean theorem. 1 squared plus the other side is 1 squared. So 1 squared plus 1 squared for the two legs equals, I don't know the hypotenuse, so we'll call it x squared. 1 squared is 1, 1 squared is 1, 1 plus 1 is 2, equals x squared. And to get rid of the x squared, I would just take the square root of both sides. So SQRT, square root of 2 equals x. So the square root of 2, also, if we put it in, I believe it's 1.41. Yep. So you could write it as square root of 2 if you wanted the decimal 1.41. So we found the length of the hypotenuse. It's a little longer than 1. It's 1.4. So that's the longest side of the triangle in a right triangle. So that makes sense. Let's see if we notice any patterns here. So that side was 1, 1, and the diagonal was 1.4. Let's make a side length that's a little bigger. Let's go to 2. It'd be 2 and 2.83. If I did the diagonal divided by the side, that's 2.83 divided by 2, which is 1.41. Let's do 3. So the sides are 3. The diagonal is now 4.24. Let's do 4.24 divided by 3, see what we notice. Oh, it's still 1.41. Let's do 5. Let's mix it up. 5. 7.07. If I did 7.07 divided by 5, I get 1.41 again. What are we noticing here? The diagonal divided by the side is always 1.41. Or the square root of 2. We just talked about the square root of 2 was 1.41. So here's the pattern that's happening. Every time we make the triangle bigger, this was 1, 1, and that was square root of 2. If we made it twice as big, it would be 2, 2, 2 times the square root of 2, right? We're multiplying this triangle by 2. So now it's 2 times the square root of 2. If we multiplied that triangle by 3, it'd be 3 square root of 2. 3, 3, 3 square root of 2. All these triangles are similar, so they follow the same pattern. So the sides are the same, the legs are the same, and the hypotenuse is the leg times square root of 2. So here's what a 45, 45, 90 is. They all follow the same pattern because they are all similar. They all have 45-degree angles and 90, so they are all similar. This is the simplest one, 1, 1 square root of 2. But we could have 2, 2, 2 square root of 2, 3, 3, 3 square root of 2. And then whatever this side is equal to this side, and then that times the square root of 2. They all follow this pattern. So it makes it really easy to figure out missing angles and missing sides in a 45, 45, 90 triangle. So let's calculate the missing sides here. So this leg is got to be equal to this leg because two angles are equal, so two sides are equal, and it's the legs that are equal. So this is going to be 14. Pretty easy. QR is 14. Now this is the side times square root of 2. Remember, it was the side times square root of 2. Well, the sides are 14. So this missing side is just 14 square root of 2. That's it. So it's easy to use that pattern. You could also use the Pythagorean theorem. Now, if we went the other way, we would just have to divide by square root of 2. So this side would be 12 divided by square root of 2.